In this lecture, we will discuss the tracking problem. In general tracking problem, the reference input is often a constant signal. For example, the position tracking problem, when an antenna is tracking the elevation angle of a satellite. Then the angle of the satellite can be modeled by a step signal that is a constant. As another example, the position control of an elevator with constant speed. To track the position of the elevator until it reaches the next level, then the reference signal can be modeled by a ramp signal. In rare cases, we have the tracking problem with constant acceleration. Consideration of these cases leads us to consider the steady-state tracking errors in stable systems with polynomial inputs. For polynomial inputs, the time function is RT is tk of k factorial. Factorial is, let me give you an example. Factorial k means k times k minus 1 times 2 till times 1. Then the Laplace transform of the polynomial inputs RT is capital RS, is 1 over S k plus 1. If we borrow the generic reference nomenclature from mechanical systems, we can call the polynomial inputs with degree 0. That will be a step signal. If k0, so RT is a unit step signal. We also call it position input. When k is 1, it is a polynomial input with degree 1. It is a ramp signal. We also call it velocity input. When k is 1, so RT is t. When k is 2, the signal is a parabola. We also call it acceleration input. In this case, RT is equal to t squared 2 factorial is 2 times 1, so it's 2. Then we can classify the control systems. We call it system type according to the degree of polynomial they can reasonably track. For example, if a control system can track a polynomial of degree k with a constant tracking error, then we call the control system is type K. Of course, the basic assumption, the systems are stable. Without stability, we cannot talk about tracking. Then the constant steady state tracking error, we call it error constant. Now let's see the basic equation. You know, in the unit step, the unit feedback, the tracking error is equal to the sensitivity function times the reference input. Here, let's assume there are no disturbances and no sensing noises. Then the tracking error is sensitivity function times the reference input. Then to calculate the steady state tracking error, we can apply the final value theorem. So the steady state of the error E is S times the sensitivity function times the reference input. So here it's G0 and D0. Then for a polynomial input with degree k, the Laplace transform is 1 over s power of k plus 1. Now let's define the forward path transfer function. It's g times d. That is also the open loop transfer function. We can define the system type according to the number of poles at the origin. Now let's write the forward path transfer function in this way. We separate the number of poles at s is 0. Then this part, G times DCL0 has no pole at the origin. If the system has n poles at origin, then we call the system is type N. Then we define a constant Kn. It's GD closed loop 0. We let S be 0. It is equal to, if we multiply Sn on both sides. It is Sn times the forward path transfer function. Then let S be 0. It is a constant. Since GDCL0 has no pole at the origin. Then for type 0 system, it means N is 0. Then the forward path transfer function has no integrator. For type 1 system, N is equal to 1. It means the forward path transfer function has one integrator. And so on. Then the tracking error becomes this S from the final value theorem. Then GDS can be written as GDCL0S over Sn. Here is the input. Then we multiply Sn on both numerator and denominator and cancel one S here. Then we have SK1 over SK, then have Sn here, Sn here, then GDCL0, 0 is Kn. So we have Sn over Sn plus Kn. Kn is a constant times 1 over Sk. That is the steady state tracking error. Now let's look at the step response. We know for step response, the reference input is a constant. The constant is a polynomial with degree 0. Then we know K is 0. So if K is 0, this part is 1. Then the steady state tracking error becomes Sn over Sn plus Kn. Now let's assume the system is type 0. If we type 0, we know G times D has no integrators. So N is 0. So K0 will be GDCL 0. We also call it Kp. It is perturbation constant. In this case, the steady state tracking error becomes when N is 1, N is 0, it's 1 over 1 plus Kp. Then for system type higher than 0, if N is greater than 0, it could be 1, 2, then the steady state tracking error is 0. In other words, if the reference input is a step signal, then type 0 can track the reference input with the steady state tracking error 1 over 1 plus Kp. Kp is a precision constant. Then for systems types 1, 2, and so on, the steady state tracking error when input the step signal, the tracking error is 0. Now let's take a look at the ramp input. The ramp input is t. The Laplace transform is 1 over s squared. It is a polynomial with degree 1. Then the steady state tracking error will be Sn over Sn plus Kn 1 over s. Then if the system is type 0, then n is 0, then Sn will be one plus Kn 1 over s. When s is close to 0, then the steady state tracking error is infinity. It means the system type 0 cannot track the ramp signal. Then the error grows unbounded. Then for type 1 system, so n is 1, so we have s plus Kn becomes K1, 1 over s, then s is cancelled, then s becomes 0, then we have 1 over K1, so K1 is also called Kv. So Kv is velocity constant. Calculate K1, it's S times G times D, the forward path transfer function. Then let S be 0. Then for system type higher than 1, for example 2, we have s squared over Kn 1 over s, then s is cancelled, then if s is 0, then it will be 0. Then we can summarize the result here. If the reference input is a ramp signal, then the type 0 system cannot track the ramp input. Then type 1 system can track the ramp reference input with a constant steady state tracking error 1 over Kv. Kv is velocity constant. Then for systems type higher than 1, the steady state tracking error for a ramp signal is 0. Now let's see the parabolic input. for parabolic input, the input is 1 over s power 3. The time function is half of t squared. It is a polynomial with degree 2. So if k is 2, the steady state tracking error is Sn over Sn plus Kn 1 over S squared. So for systems type 0 and 1, the steady state tracking error grows without bound. So if we put S is 1, we have S plus K1 1 over S squared. 1S is cancelled, so S0. So it will become infinity. Then for type 2 system, N is 2, S squared plus K2 1 over S squared. S squared is cancelled. Let S be 0. 1 over K2 is the steady state tracking error. We also call K2 is Ka, acceleration constant. So K2 can be calculated as S squared G times D open loop transfer function, then let S be 0. Then the steady state tracking error is 1 over Ka. Ka is acceleration constant. Then for system type higher than 2, the steady state tracking error is 0. So if we have type 3 system, have S3 over K3 1 over S squared. Then we have 1 S left. S is 0. It is 0. Now we can summarize the result. When N is greater than K, in this case, we have S we have 1 over Sn plus Kn Sn minus K. If N is greater than K, then we know the steady state tracking error is 0. It means a system type N can track any polynomial input with degree less than N with steady state, 0 steady state tracking error. Then if N is less than K, it means a system type N cannot track any reference input when the polynomial, the order of the polynomial is greater than the type of the system. Then when N and K are the same, the steady state tracking error is 1 over 1 plus K0. So this is 1, 0, when n is 0, as n is 1. When both n is equal to k is equal to 1, the reference input is a step signal. It's 0-degree polynomial. The constant k0 is also called precision constant. Can also be written as Kp. When n is 0, the system type is 0. When n is equal to k is not 0, then the steady state tracking error is 1 over kn. So when n is same as k, so s power of n minus k is 1, then s is 0 is 1 over kn. For example, when n is same with k is 1, then it is a polynomial with degree 1. It is a ramp signal. Then the constant k1 is called velocity constant. It can also be written as kv. This plot shows a reference input. It is a ramp signal. The bottom line shows the output of a type 1 system. Here is the transient response. Here, the steady state response. You can see the constant steady state tracking error is 1 over kV. When n is 1, it is a type 1 system. Now let's use this table to summarize the system type and tracking errors. We have some basic formulas. So G times D, it is an open loop transfer function. Depends on the number of poles at the origin, we can define the system type. Then the error constant is the part without any poles at the origin. Then let S be 0. Then the steady state tracking error is Sn over Sn plus Kn 1 over Sk. Then for type 1 system can track step signal with steady state tracking error 1 over Kp. It cannot track ramp signal and parabola. Kp is also called precision constant. It will be Gd, let S be 0. For type 1 system, it can track step signal with 0 steady state tracking error. It can track ramp signal with a constant steady state tracking error. 1 over Kv. Kv is called velocity constant. It can be calculated by times S, G times D, then let S be 0. For type 2 systems, so N is 2. It has 2 0 poles. Then type 2 system can track step signal and ramp signal with 0 steady state tracking error. When the reference input is parabola, the steady state tracking error is 1 over Ka. Ka is called acceleration constant. It can be calculated as S squared times the open loop transfer function, then let S be 0.